Great, so we have the last talk today. We're very happy to have Sarah Harrison from Northeastern University, and she's going to talk about Liouville theory and Weil-Petersson geometry.
Yeah, thanks very much for the introduction and for inviting me to speak today. Yeah, I apologize in advance a little bit. I'm not talking about anything arithmetic, though maybe someday it'll be connected. But I am talking about some quantum field theory and some math. So what I'm talking about today is mostly based on two papers with some colleagues, Alex Maloney, my former colleague at McGill, Takira Numasawa, who was a postdoc at McGill and is now in Japan, and then Coleville and Namjou, who were students at McGill when I was at McGill. I was at McGill until about a year ago when I moved to Northeastern. And basically, the main question I'm going to be exploring today is whether we can compute the Weil-Petersson metric on the general moduli spaces of hyperbolic Riemann surfaces and study dynamics on moduli space. And I'm not going to really completely answer that, but I'll be able to do some stuff for specific examples of Riemann surface moduli spaces. And the technique that we're going to use is something from physics, something called Liouville conformal field theory. So the idea is to be able to compute the metric, which we're going to end up using a combination of analytic and numerical techniques to do this, and then eventually study the spectrum of the Laplacian. And some sort of broad motivation from both physical and mathematical perspectives is that very broadly understanding spectra and dynamics on moduli spaces is very interesting. And just one example of sort of deep relations in this subject is the Selberg trace formula, which relates eigenvalues of the Laplacian on a Riemann surface to lengths of classical geodesic lengths. And you can imagine, I mean, this has many extensions, both analytic and arithmetic cases. So it's some kind of deep relation that's much broader than the connection between specifically Laplacian eigenvalues and geodesic lengths. But you can imagine exploring some similar connections instead of on Riemann surfaces themselves on moduli spaces. And we won't quite get to that level here, but sort of take a small step in this direction. So this subject has connections to many areas of mathematics, including geometry and number theory, as well as interesting subjects in physics, such as quantum chaos, random matrix theory. And very specifically today, we're going to use techniques from a specific quantum field theory and physics called Liouville theory, which has been studied by many physicists going back to sort of foundational work of Weil-Petersson, which has a deep connection to the geometry of Riemann surfaces. And so we're going to be applying sort of physical techniques in the study of Liouville theory to try and get at understanding the geometry of Riemann surface moduli spaces. And just as kind of a flavor for the application in physics, though we're not really going to touch on this today, Liouville theory is very important in studying quantum gravity in both 2 and 3 dimensions. So quantum gravity in 2 dimensions, which arises in the worldsheet of string theory, involves integrating over moduli spaces of Riemann surfaces. And then quantum gravity in 3 dimensions, in some circumstances, can be connected to sort of geometric quantization problems, where your Hilbert space lies on a Riemann surface. But I'm not really going to be talking about quantum gravity today. Okay, so that was sort of some motivation. And here's sort of the plan for the rest of the talk. I'm going to start with some very brief mathematical background about moduli spaces of hyperbolic Riemann surfaces, some of which I'll use today. And then I'll talk about the connection between Liouville theory and the geometry of Riemann surfaces, which I'm going to exploit to study, to eventually try to study the geometry of moduli space. And then as a case study, I'm going to talk about the moduli space of genus 0 Riemann surfaces with 4 punctures. Talk about how we can use a combination of analytic and then numerical techniques to compute the metric on this moduli space to a very high degree of accuracy. And then I'll talk about how we can use that numerical approximation to the metric to study the spectrum on the moduli space and briefly comment on some extensions which we looked at. Okay, so this is maybe the most mathematical part of my talk where I review some basic facts about hyperbolic Riemann surfaces, which hopefully I think some of which are familiar to you, though I don't fully understand the scope of the background of the audience, as I know it's a sort of combination of disciplines people here. So I'll start by calling sigma sub G comma n a genus G Riemann surface with n geodesic boundaries of lengths L. It's a very well-known fact that the Euler characteristic of such a Riemann surface only depends on the genus and the number of boundaries, and it's given by the following formula. And when the Euler characteristic is negative, you can prove that there's a unique up to sort of rescaling constant negative curvature metric on this Riemann surface. And there's something in math called the uniformization, which allows you to write this Riemann surface as a quotient of the upper half plane mod a group gamma, which is a subgroup of PSL2R, where this H is the upper half plane equipped with a hyperbolic metric. And in the talk, in some applications in this talk, instead of considering Riemann surfaces with geodesic boundaries of these lengths L1 to Ln, I'll consider punctures where we take the lengths to 0. In fact, my main case study will be the case with punctures rather than geodesic boundaries, or cone points where we sort of analytically continue the lengths to an imaginary number. These correspond to conical defects with an opening angle theta, which lies in this range 0 to pi. And then for each geodesic boundary, you can relate them to an element, a generator in this group gamma that appears in the uniformization theorem, where if you have a geodesic boundary, there exists a hyperbolic element in gamma. If you have a puncture, there exists a parabolic element, and if you have a cone point, there exists an elliptic element, which means that the trace of this generator is either greater than 2, equal to 2, or less than 2. And the length of the geodesic boundary is equal to half the trace of this generator via this formula. So the hyperbolic cosine of the length over 2 is equal to half the trace of this generator. If you take the limit as the length goes to 0, you get the case of punctures. And if you take the analytic continuation of this length, you get a relation which relates the cosine of the deficit angle to half the trace of this element. So in particular, if you have a presentation of your Riemann surface in terms of an explicit subgroup of PSL2R, you have some analytic formulas for these lengths or angles. So we eventually want to consider the geometry of moduli spaces of Riemann surfaces. So for a general Riemann surface of genus G with n boundaries, the moduli space has dimension 6G plus 2n minus 6. And one way of putting a coordinate system on moduli space has to do with decomposing your Riemann surface into pairs of pants. And an example diagram is given here, where if you cut this genus 3 surface along these circles, you end up with 4 pairs of pants, where the boundaries are given by these circular cuts. And then when you decompose the Riemann surface into these pairs of pants, you end up with 3 lengths. And you can glue these pairs of pants back together along these circles. And the way you glue depends not only on the lengths of these circles which you cut, but also something called the twist coordinates, which depends on how you sort of rotate the circles when you glue together. So for each cut, In this decomposition into pairs of pants, there exists a length coordinate and a twist coordinate. And these furnish local coordinates on the moduli space, and these are known as Fenchel-Nielsen coordinates. So you can take these coordinates to arbitrary real values, and then you get something called the Teichmuller space, which is a universal cover of this moduli space. And then if you quotient the Teichmuller space by the mapping class group of the Riemann surface, which sort of relates different pants decompositions, then you can represent the moduli space as a quotient in the following way. And this moduli space of genus G, Riemann surfaces with n boundaries, admits something called the Weil-Petersson symplectic structure, which can be written very simply in terms of the Fenchel-Nielsen coordinates in the following way. And in the special case where the boundaries on the Riemann surface are punctures rather than geodesics, this is a Kähler form. Actually, it's been proven by Takhtajan and Zograf that this Weil-Petersson symplectic structure is a Kähler form for moduli space for both punctures and conical defects in a certain range of parameters. But in general, for bordered Riemann surfaces where these are geodesic lengths, there's no Kähler structure. But actually, in what we're going to do, we don't make use of the Kähler structure, so we'll be able to do some numerical approximation for the metric on moduli space, even of bordered Riemann surfaces. So eventually we're going to try to numerically approximate the metric and compare to something analytic. And one useful thing we can compare to are known values for volumes of moduli spaces. So in general, the volume of the moduli space of M, G, N can be represented in the following way as an integral of the symplectic structure over the moduli space. And this in general is hard to compute in the abstract, but in some beautiful work of Maryam Mirzakhani, she proved that this volume is a polynomial in the geodesic lengths of the boundaries with coefficients, which are rational multiples of powers of pi. And she also gave a prescription for computing this volume polynomial recursively in terms of moduli spaces of lower genus. And as an explicit example, and this is the case we're going to be looking at in this talk, for a genus 0 Riemann surface with 4 boundaries, the volume polynomial is very simply written in the following way, where L1 to L4 are the lengths of the 4 geodesic boundaries. And if you take the lengths to 0, so you consider genus 0 Riemann surface with 4 punctures, the volume is just 2 pi squared. This is something we're going to be able to reproduce when we numerically approximate the metric. And even in her original paper, Mirzakhani predicted the following fact, which is that in the case where the conical defects lie in this parameter range, you can take a simple analytic continuation of this volume polynomial to get the volume of moduli space of Riemann surfaces with cone points instead of geodesic boundaries. And then this was eventually proven by these authors, if I understand correctly. Okay, so that's briefly what I wanted to say about moduli spaces of Riemann surfaces. Now I want to talk about physics for a bit. So the tool that we're going to use to try and understand geometry of Riemann surface moduli spaces is something known as Liouville theory. And this is a two-dimensional conformal field theory in physics with the following action in Euclidean signature. It's given by an integral over a Riemann surface. So you pick a Riemann surface and then you put this theory on that surface with a standard kinetic term for a scalar field phi and a potential which is exponential in phi. This conformal field theory has central charge given by 1 plus 6q squared, where q is a parameter related to this this number b in the exponential. It's equal to b plus 1 over b. And you can show that this is a conformal field theory with a continuous spectrum, so it's a little bit unusual compared to the kind of rational conformal field theories which appeared in the previous talk. And it has primary operators, which are called vertex operators, which have conformal dimension, which I'll call delta sub alpha, which is equal to alpha times q minus alpha, where it's standard to parameterize this alpha as q over 2 plus I times p, and p is known as the Liouville momentum. And basically, far away from this potential, you can represent the solution sort of as the plane waves with the momentum p, which is why this has the term Liouville momentum. And the full quantum theory can essentially be characterized by the set of endpoint correlation functions of these primary operators. So if you know all of the endpoint correlation functions of these vertex operators, you essentially have characterized the theory. And this, remember, this depends on the Riemann surface that you put the theory on as well. So there's a beautiful connection to the geometry of Riemann surfaces in the semi-classical limit of Liouville theory, which is the limit where you take the central charge to infinity, this central charge here, which you can see can also be written as taking the parameter q to infinity or the parameter b to infinity. And in this limit, you have to rescale the Liouville field appropriately. Then the classical equation of motion that you derive from that action is precisely Liouville's equation. And a solution to Liouville's equation with you have to prescribe boundary conditions at the boundaries of the Riemann surface, but once you put the correct boundary conditions on this equation, a solution furnishes a unique metric of constant negative curvature on the Riemann surface, which takes the following form. This conformal factor of the metric is just an exponential of the Liouville field. So sort of the message is that classical solutions of the Liouville equation give you constant negative curvature metrics on the Riemann surface. And in Liouville theory, the conformal dimensions of the vertex operators you consider tell you what kind of boundaries you're considering on your Riemann surface. So in the case of punctures, you that corresponds to vertex operators with Liouville momentum equal to 0. If you have either conical defects or geodesic boundaries on your Riemann surface, that corresponds to primary operators with Liouville momentum either an imaginary number or a positive real.
So,
yeah,
you explain what is how does the geodesic boundary have to do with the? I think of a vertex operator living at a point, so am I thinking of that point as living on growing a boundary circle there, or?
Yeah, you kind of shrink the boundary to a point and then consider a vertex operator living at that point. Okay, so we're going to study, we're going to look in detail at the geometry of first M04, so genus 0 Riemann surfaces with 4 punctures. And then I'll talk about, for most of the talk, I'll talk about this case, and then sort of at the end, I'll talk about generalizations to other Riemann surfaces. So first, let's talk about coordinates on this moduli space. And there are many different kinds of coordinates that you can write down, and I'll talk about some convenient ones for our analysis. So one set of coordinates are known as cross ratio coordinates. And we can specify a point in this moduli space by the locations of the 4 punctures. So let me call them Z1, Z2, Z3, and Z4, up to conformal transformations. Once you've portioned out these conformal transformations, you're left with a one complex dimensional moduli space. And it's convenient to define what's called a cross ratio coordinate in terms of the locations of these four punctures in the following way, where x is known as the cross ratio and it's just equal to some complex number. And so a particular cross ratio defines a particular genus zero Riemann surface with four punctures, which defines a particular point in this moduli space M04. And once you have a particular instance of sigma 04, then there's a unique geodesic which separates Z1 and Z2 from Z3 and Z4, which is the minimal geodesic encircling two of these points. And if this geodesic encircles Z1 and Z2, it's known as the S channel in physics. So there's a unique minimal geodesic in the S channel. And we'll come back to that in a bit. But I also want to briefly present two other coordinate systems that will be used for our analysis. So here on the left-hand side, I've drawn a picture of the cross ratio plane. So this is just a complex plane where the coordinate in the complex plane is this cross ratio x. And there's an action of a group of anharmonic transformations on the cross ratio, which divides this plane into 6 fundamental domains. And here I've shaded half of one of the fundamental domains for this group of transformations. And it's this shaded region that we're going to solve Laplace's equation on eventually with a choice of boundary conditions for each of these sides. So this is actually going to divide the moduli space into the area of this is actually a 12th of the area of the full moduli space. Because the group of anharmonic transformations divides it into 6 regions of equal area, and then I'm taking half of one of the regions. But actually, it turns out the cross ratio coordinate is not the most convenient coordinate to use when doing the physical analysis that we're going to do. So I'd like to introduce another coordinate, which is this function of the cross ratio, call it tau. And it's I times this elliptic integral of the cross ratio, this ratio of elliptic integrals. And if you do this transformation, you can show that tau lives now and lives in the upper half plane. And this shaded region on the left-hand side gets mapped to this shaded region on the right-hand side, where the red boundary gets mapped to this line, the green one to this one, and the blue line to this one. And this is similarly, this is half of a fundamental domain in the tau plane for a different modular subgroup. So we're actually going to eventually use this tau coordinate, or rather an exponential of this tau coordinate, in order to do our analysis. Okay, as I said earlier, there's a symplectic structure on M04, which leads to a Kähler metric known as the Weil-Petersson metric on moduli space. And I also mentioned this earlier, there's a theorem by Zograf and Takhtajan that the Liouville action is a Kähler potential for this metric. So if we can compute the Liouville action as a function of cross ratio, then you just have to take a couple derivatives to get the Weil-Petersson metric. Now, unfortunately, we can't compute this exactly, but we can use techniques developed in studying Liouville CFT to get a very accurate approximation of this action. And thus a pretty accurate approximation to the metric. So these techniques are very old techniques in physics, but this is a relatively new application for them. And it's sort of, I mean, eventually it's just a combination of analytic techniques developed in the study of two-dimensional CFT, as well as some numerics on top of that. Okay, so on the previous slide, I mentioned that this path integral, which leads to the Liouville action on a Riemann surface, leads to a Kähler potential for the Weil-Petersson metric. So we want to compute the path integral on sigma 04 in order to approximate the Weil-Petersson metric on M04. And the way that we can do this is by expressing it as a 4-point function of primary vertex operators with a conformal dimension chosen to be C minus 1 over 24. If you remember some formulas from a few slides ago, this is precisely the case where the Liouville momentum is 0, and this corresponds to punctures at the locations of the 4 boundaries. And this 4-point function can roughly be represented as an integral over 3-point coefficients squared times something called conformal blocks squared, and that arises from the fact that if we take this Riemann surface and we cut it along this minimal S channel geodesic, we get a 3-point function on the left-hand side between Z1, Z2, and this geodesic length. And then we get another 3-point function on the right-hand side of Z3, Z4, and this geodesic length. And then we essentially have to integrate all intermediate ways of gluing these together with geodesic lengths, and that's where these conformal blocks arise here. So we're integrating over the dimension of the internal operator corresponding to the geodesic length upon which we cut that Riemann surface. So there's basically 2 contributions, this 3-point function contribution and this conformal block contribution. Now we want to take the semi-classical limit of this expression. This is the full quantum expression. And in the semi-classical limit, which leads to a connection to hyperbolic geometry, this path integral also simplifies, and it takes an exponential form. And so the 4-point function can essentially be expressed as an exponential of minus q squared times a classical action. And this classical action also has a 3-point function piece, which I call S3, and a conformal block piece, which I call little f. And little f is sort of the semi-classical limit of these full quantum conformal blocks, capital F. And this 3-point piece is the semi-classical limit of these full quantum 3-point coefficients. So each of these interior terms in this integral exponentiates, and these are just the functions which appear in the exponential in this limit. So this 3-point function corresponds to operators of a rescaled conformal dimension due to the fact that we're taking the limit q squared to infinity. So I call little delta the rescaling of capital delta, the original conformal dimension. And in this semi-classical limit, the dimension of the punctures just becomes 1/4, and the internal dimension of the internal operator corresponding to the cut on sigma 04 has dimension 1/4 plus p squared. And these little f's, these classical conformal blocks correspond to blocks for external operators of dimension 1/4, which corresponds to punctures in the semi-classical limit, and internal dimension 1/4 plus p squared for the operator along the cut. So in the limit, the semi-classical limit, this path integral is dominated by a saddle point, which is just the derivative of the classical action with respect to the internal momentum set equal to 0. And so this saddle point momentum can be found by taking the derivative of this classical action. And so if you can compute all of these functions, the classical 3-point function and the classical conformal blocks, then you can easily compute the saddle point momentum and plug it back in to get the full Liouville action, and then take derivatives to get the metric. And then in terms of the saddle point momentum, the minimal geodesic length in the S channel that I showed in that previous picture is just equal to 4 pi times the saddle point body. So our method is to use a semi-classical expansion around the saddle point to approximate the metric by expanding these functions in a semi-classical limit using analytic techniques in Liouville theory. And you can only do this up to some certain order in your expansion parameter, and then numerically approximating from there.
So, question.
Yes.
So previously when I talked about the classical equations,
Mhm.
so in this limit, the equations do not depend on the method.
Which equation are you talking about?
But so previously about the
This-
equation, no, for
The equation of motion?
so if the equation does not depend on
On the metric on the Riemann surface? No.
more generally it will.
What do you mean by more
Yeah,
generally?
not in the same.
You mean the equation of motion that you would get from this?
Yeah.
Yeah,
So
this equation of motion, yeah, this is not, the equation of motion you get from this is not the equation I showed on the next slide. You have to take the classical.
Yeah. So in a sense, in this limit, you don't see the dependence of the. Then when you expand around it. I'm just trying to understand the simplification of the strategy that we use.
Well, I'm not sure exactly what you're asking, but the metric that I'm now talking about is not even this. I'm talking about the metric on the moduli space. Whereas this is the metric on the Riemann surface sigma.
Yes, but you expand around. You expand around the saddle point, right?
Yes, yeah,
Maybe I'm just.
yeah, maybe we can talk after. Yeah, so, yeah, so right now we're expanding around, the saddle point for the classical action, but, with these quantum corrections. Okay. And so if we can compute the classical action, then we can take derivatives and we can get the metric. So now I'm going to talk about this strategy for doing this semi-classical expansion and approximating the classical action. And we sort of have two functions to consider. We have the 3-point function and then we have the conformal block. And so the 3-point function is known in closed forms. It's some ratio of special functions, and you can expand it. For example, near the boundary of moduli space when the cross ratio goes to 0, and the saddle point momentum is near 0. And you can also expand the classical conformal block in this limit. And then if you plug in this expansion into the saddle point equation and then take a derivative and set it equal to 0, you can solve for the saddle point momentum, and the solution is given by this. It's some coefficients, and it goes like 1 over log of x bar, where x is the cross ratio. And then you can plug that into the action, take derivatives, and get the metric near the boundary of moduli space where the cross ratio is equal to 0, and you get that the leading order term looks like this. And it matches a computation near boundary of moduli space done by Wolpert. But we'd like to do a bit better than just expanding near the cross ratio equals 0, which is one boundary of the moduli space. And so in order to do that, we'll use a combination of techniques introduced originally by Zamolodchikov. And the important idea from Zamolodchikov is that you should really work in a variable which he calls Q, which is equal to the exponential of pi I times tau, where tau is the function of the cross ratio, which is a ratio of two elliptic integrals. And so, as before, I said the cross ratio lives in the complex plane, tau lives in the upper half plane, and then Q lives in the unit disk. So if we expand in Q, you actually get an expansion for the classical conformal blocks, which very rapidly converges in the interior of the unit disk. This has been used by physicists for many years in computing conformal blocks for other purposes, but I guess this is the first time we were using it to try and approximate the metric on Riemann surface moduli space. So now we can actually write our saddle point equation in terms of an expansion of two terms, the 3-point function term and the conformal block expansion. And it turns out to be convenient to introduce an expansion parameter in terms of the Zamolodchikov Q variable, which I'll call epsilon, and you can show that you can basically solve this order by order in this epsilon variable, and you can also do some numerical checks to see that as you expand in this variable, it's sort of converging to something. So if we expand the 3-point function, first we expand in the Liouville momentum, and this expansion has been computed before by these authors, and then you can also expand the classical conformal blocks using the recursion relations in this Q variable due to Zamolodchikov, which is extremely rapidly convergent. And you can write your saddle point equation in the following way. And then if we expand our saddle point momentum in terms of this epsilon parameter, we can solve it recursively. And if we, for example, expand up to order epsilon to the 8th, so this epsilon sort of controls the expansion of the 3-point function piece. And yeah, so we sort of have an expansion in two steps. So we have a 3-point function piece expansion, and then we have a conformal block expansion as well. And so what we do is we pick an order in this Q expansion of the conformal block, and then we define an epsilon, and we expand our 3-point function. We expand our saddle point momentum in terms of this epsilon. And so if we take just the leading order in the conformal block expansion, we get an expansion for the Weil-Petersson metric in terms of this epsilon. And then if we pick the next to leading order expansion in the Q expansion and keep, say, the leading order in epsilon, we get another expression for the metric. And we can sort of do this order by order in both the Q expansion and the expansion in epsilon, in order to get an approximation for the metric in terms of this Q parameter. So with this technique and enough computing time, we can approximate the metric up to our desired level of accuracy. But as I'll show you with some plots, this is very rapidly convergent for Q in the unit disk that we don't actually need to go very high in this conformal block expansion to get something which is converging to certain analytically known quantities. Okay, so I'm going to show some plots now. Given that we have some analytic approximation to the metric, we can now plot various things and just see what they look like. So in the cross ratio coordinate, if you plot the metric, this is what it looks like. Well, we're just plotting the Weil factor of the metric, and here's the real part of the cross ratio. And then here's the imaginary part, and here these sort of cusps are near the boundary of moduli space at x equals 0 or x equals 1, where the surface degenerates, where two of the punctures come together. And here we included up to some very high number of terms in the 3-point function expansion. Okay, but more specifically, we can compare to node analytic values of various quantities in order to sort of gauge the accuracy of our metric, because eventually we want to do more with it, so we want to see how close it is to reproducing known analytic quantities. So here is a table which shows the approximation to specific geodesic saddle point lengths at specific values of cross ratio. So here in the first column, at cross ratio x equals 1/2, there's an analytic solution for what the saddle point geodesic length is. If you take the hyperbolic cosine of this quantity, you get a nice number. So in the case of cross ratio 1/2, if you take the cosh of 2 pi times the saddle point momentum, you get 3. Here we have the cross ratio e to the pi I over 3, and if you take the cosh of this, you get 7/2. And then in the third column, we have the volume of M04, which we saw previously was 2 pi squared, which is approximately this number in the decimal expansion. And here we have, using our numerical approximation to the metric at different orders in this epsilon parameter, the numerical values we compute for these functions of the saddle point momenta and the volumes. You see that when we go finally up to epsilon to the 60, we get up to accuracy up to something like 10 to the minus 5. So this includes expanding the 3-point function piece up to this epsilon parameter to the 60, and only up to order q squared in the conformal block expansion. So we see that already when we just take one subleading order in the Zamolodchikov expansion, we get analytic results to extremely high accuracy. Okay, so now that we have a numerical approximation on the metric, we want to do something interesting with it. And what we wanted to look at was the spectrum of the Laplacian on moduli space. So the idea is to use our approximation for the Weil-Petersson metric to numerically solve the Laplace equation to find a set of eigenfunctions and eigenvalues, which you can imagine describing a particle moving on the moduli space of genus 0 Riemann surfaces with 4 punctures. And so we'll solve this Laplace equation numerically, given our numerical approximation to the metric, in the shaded half fundamental domain I showed you earlier in the tau plane. And then on the boundaries, we impose Dirichlet boundary conditions, which captures only a sector of solutions to the Laplace equation that's totally antisymmetric. And so we're ignoring some other sets of eigenfunctions with various different boundary conditions like Neumann or combinations of Neumann and Dirichlet. But at least, so these are sort of the easiest boundary conditions to impose, but it will give us a sense of studying the statistics of the spectra in this sector. And then here I wrote some details about the numerical method, which are not too important, but we showed that we sort of played around with the ND eigensystem function in Mathematica, which discretized this fundamental domain and changed the discretization in various ways to see how stable the eigenfunctions were, and they're pretty stable up to 1 part in 1,000 and sort of changing this discretization. So I would say I wouldn't I would say they're pretty stable. Hopefully, the comparison of the numerical metric to analytic results gives you some degree of confidence in the accuracy of the values, but I wouldn't say that they're the study of the statistics is completely conclusive, as you'll see. So just for fun, here's a list of the first 100 eigenvalues we computed. I don't really have much to say about that except to show that we got a bunch of numbers of eigenvalues. But for maybe even a little bit more fun, here's a visualization of the ground state eigenfunction, the 5th excited state and the 40th excited state in that half fundamental domain of the tau plane. And I don't really have any explanation of these local maxima and the number of nodes or anything, but this is sort of cut off, so I imagine there's probably 5 such nodes. But it's just kind of fun to visualize given that we're getting some actual data. But with with this list of eigenvalues, this is the first 100. We actually computed the first 200 and tried to do some statistical analysis with them to see if we could say anything about what's going on in terms of the spectrum on moduli space. And so we looked at a few different things. So firstly, there's something known as Weil's law, which tells you about the asymptotic density of eigenvalues as a function of energy in quantum systems. And it's sort of a universal formula, whose leading term says that the number of eigenvalues less than or equal to of energy less than or equal to E is equal to the area of the manifold over 4 pi times E plus a subleading piece, which is the length of the boundary over 4 pi times root E with minus or plus depending on your boundary condition. So we had Dirichlet, and I think there's a minus there. And plus K, which is some non-universal constant, which depends on details of your manifold and other things. And so here we plotted the number of eigenvalues of energy less than or equal to E. And so there's actually 2 lines here. There's like a cumulative density coming from our numerical results in blue, and then a fit to the Weil's law, which is in red. And so I've zoomed in a little bit here to see that this blue part is not actually a curve. It's a bunch of steps coming from our numerical data. And so we see that this Weil's law fits very nicely to our numerical eigenvalues. This number 0.1292 in front is equal to the area over 4 pi. Remember, the area of the moduli space is 2 pi squared, but we're actually considered a 12th of the moduli space because we consider that half fundamental domain. So 2 pi squared divided by 12 divided by 4 pi is pi over 24, and that's about 0.13, which is this first number. Okay. Then we looked at two other quantities which capture spectral statistics in quantum systems. One which captures short range correlations of eigenvalues, and one which captures long range correlations. So in the so here, just for sort of background, I've written the joint probability distribution for eigenvalues that arises from a random matrix ensemble, and it contains an exponential term which depends on the potential for your random matrix theory, which is some non-universal part because you can change your potential, and then it includes this van der Waals determinant part, which is a universal part, which captures the universal feature of eigenvalue repulsion in random matrix ensembles, and this exponent beta is different depending on the kind of ensemble you're considering. There are 3 main ensembles of random matrices: the Gaussian orthogonal, Gaussian unitary, or Gaussian symplectic ensemble. If you consider a quantum system, which is in the universality class of a given random matrix ensemble, the kind of symmetries that your system has sort of picks out which one of these ensembles you consider. And given the boundary conditions we were considering, and lack of time reversal symmetry, if our theory was in a random matrix universality class, we would expect it to match statistics of the GOE. And so then we studied, there we go. Then we studied short range correlations by considering something called an adjacent gap ratio, which basically captures the statistics of nearest neighbor eigenvalues. So if we define this R sub n to be the difference between the n plus 1 eigenvalue and the nth eigenvalue divided by the difference between the n and the n minus 1 eigenvalue, there's a sort of universal behavior of the distribution of this adjacent gap ratio for each of these three random matrix ensembles. The average of this ratio can be reproduced by the following integral, where the probability distribution of this ratio is given by one of these functions for the three different random matrix ensembles, and I also listed Poisson distributed eigenvalues as well for comparison. So given that we have a bunch of eigenvalues, we can also compute this adjacent gap ratio and compare with the predictions from random matrix theory. So we don't have enough eigenvalues to get a really fine-grained plot, but sort of, I guess my pointer is generally, if we plotted with some binning the distribution of our adjacent gap ratio and compared to the probability curves that you would expect from the different random matrix ensembles, as well as the average of the gap ratio as the function of the first n energy levels. And here I plotted n from 0 to 100, and also compared the average you would get from various random matrix ensembles. And again, the number of eigenvalues is not so great to say anything very definitively, but it looks like perhaps it's not inconsistent with statistics that you would expect from something in a GOE universality class. I won't say anything more definitive than that, but it looks, I wouldn't say that you can rule it out. Okay. So I'm almost out of time. So I think I'll end by briefly mentioning long-range spectral statistics of our eigenvalues, very briefly. A common thing in, I guess, the field of quantum chaos is studying something called a spectral form factor, which is this defined as a square of an analytically continued partition function. And this quantity captures long-range correlations of your eigenvalue spectrum. And you see it has, so it's basically you analytically continue your parameter to you have an imaginary timepiece, and this exponential factor oscillates rapidly when you take t to infinity. And so it's common to average this function in order to get a smooth curve for this form factor. And if you're considering a theories drawn from some statistical ensemble, like you have a statistical ensemble of Hamiltonians with parameters that are drawn from an ensemble, or you have a random matrix theory, you can average this thing over draws in your ensemble. But we just have one theory and one set of eigenvalues. So and then you instead of averaging over draws from an ensemble, you can average over time windows in the following way. This is called the time average spectral form factor. And in order to get our smooth curve, we'll do this time averaging for our set of eigenfunctions in order to compute this thing. Now, physicists in both condensed matter and then more recently in the high energy community have discussed the universal behavior of this spectral form factor for quantum systems, and it's sort of characterized by different regimes in the time parameter. There's initially a slope where it decays exponentially, and then it reaches a local minimum, and then it has a linear increase, which is called a ramp, and a plateau where at late times it becomes a constant. And each of these pieces sort of has a physical interpretation. The initial decay is called thermal relaxation. The ramp part arises from the long distance repulsion of eigenvalues. So this form factor roughly computes the 2-point correlation of the density of states, which in random matrix theories goes like 1 over e minus e prime squared, and if you take the Fourier transform of that, you get a linear growing function of time. And then the plateau arises from the discreteness of the spectrum, where at late times, this form factor goes to some constant where only the eigenvalues with En equals to Em are contributing, because all of the others oscillate rapidly and sort of cancel out. And in our time average form factor for our eigenvalues, you can see precisely this behavior where there's an exponential slope down, some local minimum, a ramp up that looks like it might be linear-ish, and a plateau which looks like it might be leveling off. So again, it would be nice to have more accurate numerics, but it looks at least like this is not inconsistent with the behavior of a quantum chaotic system. Okay, so I'm going to skip the last part, which talked about generalizations to geodesic boundaries and conical defects. We again compared with some analytic results for our metric, and we're able to reproduce volume polynomials very accurately, but we did not analyze spectral statistics in this case, which would be interesting to do. So finally, I'm going to conclude by just briefly reviewing a few things. So our idea was to use conformal field theory techniques to study Weil-Petersson geometry for moduli spaces and Riemann surfaces. And I talked mostly in detail about this case study of M04, where we can compute the metric to pretty high accuracy by approximating the Liouville path integral in a semi-classical limit and using physics techniques to do a conformal block expansion. And as I briefly mentioned, you can generalize to other complex dimensional Riemann surfaces, such as surfaces with 4 geodesic boundaries, surfaces with punctures, or even a slice of the genus 2 Riemann surface moduli space, which has Z3 symmetry. This slice is also 1 complex dimensional. So we investigated this in the second paper. And pretty accurately reproduce quantities like volumes and geodesic lengths. And you can also try to quantitatively, though numerically, study spectra on moduli space, which we didn't somewhat level detail for M04, and would be very interesting to generalize to these other moduli spaces to try to probe evidence of as a toy model for quantum chaotic systems. So it'd be very interesting to explore some of these directions further and generalize to other moduli spaces. And I'll end there. So thank you very much for listening.
I'm not sure, maybe you said this, is there a reason from the physics, from the Liouville theory, that we might know that we should expect like a GOE kind of behavior, or?
So I think the Dirichlet boundary conditions break time reversal symmetry, so we should be expecting, I think it's a matter of the boundary conditions that we're imposing on our system. So we shouldn't, so the GUE generally has time reversal symmetry. And the GOE doesn't. But beyond that, I don't really have that much to say. Yeah. I guess. Why should we expect a quantum chaotic system in general? I guess most quantum theories are random and very few are integrable, so it's probably not surprising, but that's that we find some of the hallmarks, but then again, if you have, not to knock the analysis, but if you have even slight inaccuracies in something you're computing numerically, it's probably not hard to find something which looks chaotic, because if you take any maybe set of eigenvalues from an integrable system and add some noise on top, you'll lose that behavior. So I would just say it'd be more interesting to get results that are even more precise and see if it